Okay,
I
so
heard a
this
little
week we're
how
going to
big.
talk about how to um, how to basically take everything we've done and put a signal on the air. So the first and simplest thing is going to be a CW beacon, and the reason for that is because um, all we're doing is we're actually turning on the SI 51 for a DIT and a DAW, and so we basically enable it and disable it for the length of a DIT, and enable it, disable it for the length of a DAW. So let me switch over here to the desktop. So I found this gentleman who put together a very simple CW beacon, and so I took his code, and we'll kind of go through it. Um, so what he's doing here is he sets up a fixed
Could you make it a little
frequency.
bit larger, Jim, please?
Yeah, does that work
That's good.
better?
Oh yeah, perfect.
Okay. So he sets up his cow factor. Um, so the duration is the duration of a dit and a doll in milliseconds. So the lower the duration, the faster your dits and dolls are going to be. The higher the duration, the slower it's going to be. And then he also uses up here a speaker um, that he puts on GPIO 10, and then he also sets up a LED to show that it's transmitting. So this hertz here is going to be the tone that the speaker is going to kick out. And then he sets up a message here. Um, basically his call sign, the locator, what his power is, what his antenna is. Um, and then in his setup, he just goes through and does pretty much the same thing that we would do. You do have to set the pin mode for the output so that when you raise it high or low, it will actually be an output, which will basically uh, set the voltage to 3.3 volts. And then when you set to low, it'll set it close to zero. And then our normal initialization here for a NIT here, where you basically set up the initialization, you set your correction factor, you tell it that you're using a fixed phase loop link, and then your target frequency for the clock. We're going to make ours a little bit different because we're going to use our VFO so that we can tune it around, and then we're going to use a short press and a long press to actually kick off the message. Um, so we're going to just work on it, but then he's also created functions here for processing the message. So he takes your message, and then he breaks it into characters and then sends it out, and then he does a very like a 5-second long tone after the transmission, and then he turns the transmission off. So let's go down here to the CW function real quick. Um, so what it's doing is whether it's true or false. If it's true, it's going to enable the output of the clock. So that'll turn the clock. That'll actually turn the phase lock loop on, and you'll get your signal out, just as if we were using a key and pressing down. So we're doing the same thing here. It's enabling the clock, and then when the and then he basically turns on the pin so that the LED comes on, and then he sends a tone out on the speaker pin, whatever the hertz frequency is. If CW state is false, then he's going to basically disable the output, um, and then set the LED pin to low, so it'll turn off the LED, and then he'll then stop the tone on the speaker. Now and just to kind of show you the dits and the DAWs here. So he basically turns on the clock. He delays whatever our bit width is, and then he turns off the SI 53, and then he waits on the duration. For the DAW, he's basically turning it on and then delaying for 3 times the duration, and then turning it off, and then delaying for the duration. So that gives you, you know, a distance between a dit and a dah. And then if you're doing a space, he basically does 2 because you already have 1, so he only does a delay of 2. And then for a word, he's basically doing a delay of 6, which would give you 7x your pause between your words.
How is duration defined? Is there a definition up there
No,
in
he's just using milliseconds. So it's actually so he's using 85 milliseconds for the length of a dit.
is that
And
kind of
So if you can change the speed by changing the duration of the dit, and it'll speed up or slow down, like just like changing word per minute.
Yeah.
yeah, and I think 85 is probably right around between 15 and 20.
Okay.
That's pretty slow, yeah.
Yeah. So let's go over to Visual Studio, and I'll kind of walk you through the changes I made. So this is the same, basically the same as the VFO. It's just that I added stuff in here for the CW stuff. So at the top, we've got our calibration factor for the SI 5351. And actually what I did today while I was testing is I tuned my radio to 20 meters at 14,000 megahertz, and then adjusted my calibration factor until my CW signal was at its loudest point. So you can actually use your radio to do your calibration, especially if your radio can tune to 10 megahertz. But you can also modify the frequency in the calibration program if you don't have one that can receive it at 10 megahertz. Then we have our global OLED screen definitions. And then we've got our frequency divisors that we used before for formatting the frequency. And then we have I've used GPIO 14 and 12 for the speaker and the LED. And I've kept the duration at 85. I've set the tone to 600. And then I went in and programmed my message to be DEK5VZ with my locator, and then what antenna I would be running it from. Then we initialize the OLED display like normal. And then we basically have our definitions. Can you guys see this okay, or do I need to bring this up a little bit more?
It's fine for me.
I'll make it a little bit bigger. Matter of fact, I'll just close this for now, and we'll hide that so you guys can see the screen.
Oh, that's better.
So we've got our encoder pin GPIO 5, GPIO 18. And remember, if you want to turn this around so that when you turn it to the right, you want this to be 18 and the other one to be 5. And then our button pin is 19. And then since we're hooked up, is connected directly to 3.3 volts, we set our VCC pin to -1. I left the steps the same. Now I do have this short press after milliseconds. So if you press a button for less than 50 milliseconds, or for at least 50 milliseconds, it'll be considered a short press. If you press it for a second, which is 1,000 milliseconds, it'll be considered a long press. And you'll see in the code where I'm using the timer ticks to count that. So as long as the button's been pressed once and it comes back through, it'll check it, and depending on how long between those two presses, then it'll consider to be a short press where we change the bands, or a long press where we actually start the CW message. And we set up our rotary encoder like normal. The bands I kept the same. Our modes are the same. I just changed the current mode to CW, and I set my current band to actually 20 megahertz. You got to remember that we count from 0, so this would be 160 would be 0, 80 would be 1, 40 would be 2, and 20 would be 3. And if you wanted this to always pop to a particular frequency that you wanted to transmit on, you could do that as well. I looked to see if there was a stated frequency for beacons, and the only ones I know are the normal CW beacons that you can tune into. But I didn't see anything that they say you should be running your beacon on a particular frequency.
I think there's a band plan out there for beacons. If I remember right, I think I've seen some charts with beacon allocations in there.
Yeah. Well, if we go to the considerate operators, you've got like let's say let's go to 1400. Oh, okay. So we could set it at 1495 but I think those are international, aren't they?
I don't know that that's international. It's up there in the data part of the band plan. I don't know what that IBP and CDXF beacons are.
Well, those are the beacons that are the International Beacon Network.
Okay.
And so there's like I think 12 stations that are internationally that beacon every hour, or I think it's like every 10 minutes or so. And they start out at 100 watts and then they drop down to 10 and then to like a watt. And they just wait and then they do it again and do it again. So I was like, well, we don't want to step on that. Oh, wait, I get, so that's 14100 for that beacon. So that's a separate, but for right now, I'm just basically doing it on the end of the band.
Yeah. Okay.
But you could go in and change it.
So you're right now you're set up at on 20 meters at 14.
14.0.
This is 14.0.
Yeah.
Okay.
Hey Jim, to answer your question on that milliseconds from earlier, 85 milliseconds is 15 words per minute. 45 milliseconds is 25 words per minute, and 35 milliseconds is about 33 to 35 words per minute. So you just by changing that value, you're changing the length of the DIT essentially, which is the basis for all the other.
Well, let's do something for that. Let's go down here and let's.
So if you want to make that, you want to be that 25.
Jim, I had just one comment.
Yeah. Go ahead.
You're losing packets, Jim.
Oh, I am. Can you hear me now?
No, it's not Jim. He hasn't broken up any.
So Roger, I was going to have you give me those again, and what I'm going to do is I'm going to basically put them in here with a.
Okay. So 85 is 15. 45 is right around 25.
Okay.
And 35 is 33 words per minute. 33, okay. 30. I mean, it's not exact, but it's close. I mean, you can do the math on it, figure it out. But so 50 milliseconds would be between 25 and 33 words per minute. So it'd be 28, maybe 28, 29, 50 milliseconds would be. So just interpolating, Okay. That's the three I know about off the top of my head. So.
Well, we'll put those in there, and that way you can comment out the 15 words a minute and put it in at 25 or 33.
What we probably could do is just put the formula in there for the words per minute versus the speed, and just let them figure it out themselves.
Be good.
Yeah.
Jim, I just had one comment on the frequency. It probably wouldn't be good to go right on the edge of the band like 14.00 or 14.0, because we don't know what the calibration is on these. We could be out of band and we might get flagged. Somebody might get flagged for that.
So do we want to do like maybe 10 megahertz or 10 kilohertz up? Or do we want to do 100 kilohertz up?
Oh no, that just probably a kilohertz would be more than enough.
Yeah, I think 1,000 hertz would be more than enough because this is narrow band
So
signal.
so then 14001 would be good, right?
That's
Yeah,
100 hertz.
Okay. So it should be 10.
Yeah, there
yeah,
you go.
Okay.
yeah.
So I'll do that with all these just so that we can make sure that we're up 1 kilohertz.
Yeah.
Now you're gonna make me have to go back and change my radio because I had it all set up.
Well,
That's a good idea, though.
yeah,
No, that's to me that's plenty fine. That's why I was asking because again I was looking and looking, I couldn't find anything. Okay,
Yeah,
so
almost never transmit right on the edge of any band, just in case your radio is, something went wonky and you're more than a few hundred hertz out.
we got some
yeah,
official stalkers out there now, so observers, official
yeah, that's
observers.
true. We do. They've been making
They're pretty
arrests.
active. Yeah, they're pretty active, actually.
Yeah. Um, well, and right now at 10 milliwatts, that's one of the things I was playing with is everything was up and up and up, and I had to bring it down onto frequency. So, um, but I did notice that just using like the little tiny SA and my cheap Chinese frequency counter, I was starting off by about 700 or about 7 kilohertz higher than what it was reading, which is good. I was always in the band, but
Yeah, it's good to be off that way than the other way. Yeah.
yeah. Okay, so the next thing is I brought up all the function prototypes up here so that if a function that we write makes a call to it, they will have been predefined for it. So here's all the rotary encoder functions. Here's the SI53 functions that basically inits it and sets the frequency. Here's the OLED display functions. And then here's all the CW beacon functions. And what we're going to do also later on, after I go through this and we play with it a little bit, I'm going to walk you guys through how to take this stuff and move them to their own files so that you have your functions separated. Because this thing now, if I go down to the end, we're like 600 lines long, or 566 lines long, and every time you got to find a function or make a change, you've got to jump up and down and navigate through it. So this is what they would call an anti-pattern, that all your functions are in one file. And so what we're going to do is we'll walk through how we can create a separate CPP files that will get loaded in and compiled. So we'll break these out. So our setup, we're going to initialize the serial port to 1,115 kilobits per second. We're going to set the mode for the LED pin. Then we're going to initialize the display, and if it fails, then it'll just print out an error message and stop. And then we're going to basically pause like we did before. We set our target frequency to whatever the current band is and the current frequency. And then I broke the rotary encoder code and the SI53 code into their own functions. So now we have a function called init rotary encoder and then init SI5351. And then our loop stays the same. We go through our rotary loop, we go through our display loop, we set the frequency, and then we delay 50 milliseconds. And so here in the rotary encoder stuff, we've got our init rotary encoder. So we tell it to begin, we set it up with the ISR routine, and then we basically set the boundaries and the encoder values like we did before with our low end of the band and our high end of the band. And that fact that we want to circle values false. So we want to stop when we get to the either end of that. And then set the current frequency based off of the current band. and then disable acceleration and set our accelerations to 250 so that, if you can do 1 kilohertz steps, or you can make it jump. And then we have 2 new functions here now called on button short click, and it's going to call handle band change, and then on button long click, which is going to call send CW message. And then we have this new function now called handle rotary button. And so what we're doing is every time we come into here and the button was pressed down, we're going to save off the time in milliseconds from the system clock. And then we're going to also use the was button down flag to determine whether was the button down last time I was in this function or not. And then we use the function here is encoder button down. That'll give us whether the button's been pressed or not. And then based on that, it's going to say if it's down, then we're going to say, okay, our rotary button's down. If it wasn't down before, then let's just save off the last time the button was down and say the button was down, and then return back out of the function. If the button was down, then it's going to take current millis versus the last time the button was down. And if it's greater than the long press after milliseconds, which was 1 second, then it's going to call on button long click, which will send the CW message. Else, if the millis minus the last one is greater than the short press after milliseconds, then it's going to do the on shorten button click, which will change our band. And then once it's done, it will basically drop out and set that back to false because it has already processed a button down. And so now the next time it comes into this, if you're doing quick single button clicks, then it'll pick up each click. And then we have our handle band change, which was in the old on button down, where we increment the current band. If it's greater than our band switch max, then we set it back to 0. We print it was changed to such and such meters, and then we set the new boundaries for the rotary encoder and the new value, and then we set the target frequency to the current value. And our rotary loop really hasn't changed much. We're still, if the encoder values change, we're printing it and we're updating the value and then setting the target frequency. And then we're just making a call here to handle rotary button. I found in my testing that this was actually keeping it from getting called, so I just commented that out. So we're just going to take that out. It's no longer needed. So at the end of the function, every time it gets called, it will basically walk through this and check on it. And then we've got our the ISR, which basically reads the encoder stuff. Every time you make a change to the encoder, it'll basically handle that. So the next thing is our SI5351 functions. And the first is we just took the code out of the setup and moved it down here. So we're doing the same thing. We're setting up the crystal. We're setting the correction factor. We're setting the phase lock loop. We're setting up our target frequency. And remember, we have to multiply it by 10,000 in order to get into hundredths of a hertz. And we have to use ULL to keep it, to make sure it goes to unsigned 64-bit. We set the frequency, and then we make sure that the output is disabled. Otherwise, what happens when it comes up, it's going to come up and it's going to be transmitting on that frequency. And in this case here, we don't want to transmit till we set the frequency to what we want and then press the actual rotary button, long press. And then I just move this code here so that anytime we want to set the frequency, we don't have this sprinkled all over the place. We just call this and we multiply it by 10,000 and then call set frequency to change the frequency. And then we've got our old OLED display, which nothing has changed here. It's still the same. I just got rid of the serial printouts because if you're looking to see the other stuff, the frequency popping through every 50 milliseconds makes it hard to find messages. But I left them in here so that if you wanted to debug stuff, you could. And we got our display band and our display mode. Now, the other thing we could do, we've got enough space on the display, we could actually have a display transmitting message. We would just have to set the text to add another 12 pixels to it. And then we could put display mode is transmitting or is not transmitting, but we can do that later if we have plenty of time. And then we've got our display loop, which basically goes through here and clears the display, displays the frequency, displays the band, displays the mode, and then shows the display. And now let me expand these all. So the send message, it basically goes through and calls CW string process with the CW message that we have at the top. It waits for a half a second, and then it basically plays a 5-second long tone, and then it shuts it off and then waits for a second, and then it returns out. And then here's the code that actually processes the message. So what it does is it walks this string starting at 0 until whatever the length of the string is, and it basically just calls CW character process, which then goes through and decides here it says, okay, if it's a space, then we call word space, which means it's going to basically space it out, 6 durations long. Because we want to keep everything in uppercase because that makes it simpler to switch. It looks at the ASCII character, and if it's greater than 96, then it and less than 123, then it basically sets and subtracts 32 to put it back in the uppercase mode. And then what we do is we're going to basically, based on the characters, we're going to basically send dit dash and then a space. The hashtag is used for space. So it basically populates that string. And so it's got every one of the characters with each one of the dits and das for it. And the numbers, and then all the pro signs, question mark, equals, comma, slash. And then what it does is it basically goes through and walks through, it can be up to 7. And then it just basically says, okay, if I got a dit, then call the dit function. If I got a dash, then call the da function. If I got a hash, then call the character space. And if there's nothing there, it will just basically skip over it. And S, if you actually look up here, I think it's a character array that's 7 long. It's just a string. So that basically will then call the dit and the da. And I think we went over this earlier. It basically tells it to enable the transmitter or the SI53 clock so the tone comes out, waits for the duration, and then turns it off. And the DAW does 3 times the duration, and then turns it off and then delays. And then your space delays 2 times the duration, and then your word space 6 times the duration. And again, that's because they're basically doing a delay after the dit and the da of duration. So we do 1 less so that our spacing's that off. And then down here in the CW, again, if it comes in as true, then we enable the clock output. We turn on our LED and we play our tone. If it's false, then we disable the clock output. We set our LED to low and then off. So now what I'm going to do is I'm going to switch over here to the overhead view, and I'm going to deploy this.
Do you have to recompile that now first, Jim, since you made those code changes, or?
Yeah, actually, when you do deploy, it compiles it, right? And then uploads it. So you don't have to do a build. You can just do a deploy, and it'll take care of it.
Okay.
But usually, if you make a lot of changes, you do want to do a build just to make sure that it works, right?
Okay.
Now I'm going to turn on my radio here.
What frequency are you on?
I'm on 14.001.
14.
So I'm gonna go up to 14.001. And now we can still step through it, but I'm gonna just hold it in right now for a second. Oh, I wasn't fast enough. Let me go back. I was too short. Can you guys hear that?
No. I got my radio on. I'm trying to hear it too.
Oh, I don't think I.
Like, do you have this on an antenna?
My antenna is this piece of wire.
Okay.
We don't hear it.
You're not hearing that?
Uh-uh.
Do you have original sound on, Jim?
Well, it's playing through my mic. I'm surprised you guys didn't hear it through my mic. All right. Well,
Jim, what's that black thing? That black circle there, right above the green
oh,
neon.
that's a little piezo speaker
Oh, okay, got you.
that I just added there so that I could hear it while I was testing.
Okay.
Make sure that it was actually playing, and then the little LED, to show you what it's sending.
Yep. Good.
All right, let's go back over here to the desktop. Maybe it's actually OBS that's filtering it out.